So a thing you'll remember doing in discrete time is hitting times, hitting probabilities, and expected hitting times. So in continuous time, you'll remember we talk about the jump chain, which is where we move to, and the exponential waiting times, which is how long we wait in a state once we get there. So for hitting probabilities, the probability of hitting some state starting from another state only depends on where the moves are, not what time they're made. So that only depends on the jump chain, so we'll see that that's exactly the same as discrete time. For expected hitting times, because that's an expected amount of time, that does depend on how long we wait in a state. So that will be a little bit different than it was in discrete time. So let's look at the details for those now. So just as a reminder of the notation we used was the hitting probability was Hij, that's the probability that starting from I, you at some point in the future hit J. And similarly, expected hitting time, the notation we used for that was this Greek letter eta. Eta Ij, that's the probability that starting for I, the amount of time until you hit J, which will be infinite unless Hij is 1. And so we'll use the same notation in continuous time. And you'll remember that the way we found these in discrete time was a two-part process. Right, part one was we wrote down equations by our old friend, conditioning on the first step. And then step two was we solved those equations. And it will work the same here. It will turn out that hitting probability is nothing to do with time, it's just whether we get there or not. So hitting probability will be exactly the same as discrete time, because the time doesn't come into it, it's all about just whether you hit or not. Whereas the expected hitting time, that does involve time, so that will be a little bit different. But I think the best way to explain this, rather than doing any fancy theory, is just to jump straight into an example. I think it will be clear what's going on when we see an example. So let's go back to this example we were looking at in the previous section. We had this state here, where that up there was A2. And just because it will be useful, I am going to write down the transition probabilities in the jump chain. You might not need to write them down, you might just be prepared to work them out as you go. I'm just going to remind myself, zeros die on the diagonal, and then make sure the rows add up to 1 by normalizing them, except this funny state 3, which is an absorbing state. So when you have an absorbing state, the only sensible thing there is to make it 0, 0, 1. So those are the transition probabilities in the jump chain, which we called R. And so let's say we want to find the hitting probability H21. That is, starting from 2, what's the probability that we hit 1? And so we just do exactly the same thing we did in discrete time, looking at the jump chain. That is, we condition on the first step. So H21 is, well, with probability 1/3, we hit 1. And with probability 2/3, we hit 3. So this is 1/3 H11 plus 2/3 H31. Exactly the same thing we did in discrete time. H11, what's the probability we hit 1 if we start from 1? Well, we're already there, right? So that has probability 1, so that's 1/3 times 1 for that first one. And then H31, well, once we're at this state 3 over here, we stay there forever, right? So that hitting probability H31 is 0. So this is 1/3 times 1 plus 2/3 times 0 equals 1/3. All nice and easy, same as discrete time. Let me erase that to make some space, and then we'll do an expected hitting time, which will be a little bit different. So let's say we want to find the expected hitting time eta 1, 3. Find eta 1, 3. So remember, that's the expected hitting time starting from state 1 to hit state 3. So we're going to do the same idea, conditioning on the first step, but look out for where it's different. So eta 1, 3 is, well, because this is a time, we have to take into account how long the current step takes. Now, in discrete time, the current step takes time 1, right? We always started with 1 plus. But how much time are we going to spend in state 1 on average? Well, in state 1, we're going to spend a time that's exponential with rate 2, right? Spend time exponential 2 in state 1. And remember, exponential with rate 2 means the expected amount of time is a half. So expected time in state 1 before moving, before jumping, is equal to a half. So here we have to allow for a half time we spend on average in state 1. And then in fact with certainty we move to 2, don't we? We move to 2 with certainty, then we have eta 2, 3. So we conditioned on the first step, but instead of doing 1 plus for the 1 discrete time step, we had to do a half, because a half is the expected amount of time we spend in state 1. So similarly, we've got an equation there that has eta 2, 3 in there. So as we've always done before, we need to write down an equation for eta 2, 3 by conditioning on the first step. So the amount of time we spend in state 2 before moving is exponential with rate 3. So that has expectation 1/3. That's 1/3 for the expected amount of time we spend at 2, but then we condition on the first step, right? We go down to 1 with probability 1/3, up to 3 with probability 2/3. So that's going to be, that's 1/3 eta 1, 3 plus 2/3 eta 3, 3. But of course, eta 3, 3, the amount of time to get from state 3 to itself is 0. It doesn't take any time, we're already there. That's 1/3. 1/3 eta 1, 3. And so now we have these two equations, right? We have this equation involving eta 1, 3 and eta 2, 3. And we have this equation involving eta 1, 3 and eta 2, 3. And thus, we just need to solve these simultaneous equations however you like. The way I'm going to do is I'm going to substitute number 2 into number 1, but whatever way you prefer to solve simultaneous equations is fine with me. So subbing 2 into 1 gives eta 1, 3 equals a half plus 1/3 plus 1/3 eta 1, 3. So that comes out to 2/3 eta 1, 3, taking that eta 1, 3 over to the left. A half plus 1/3 is 5/6, times by 2/3, 3 over 2, that will give me 15 over 12, or 5/4. So we'll get 5 over 4 for the answer. The expected amount of time to get from 1 to 3 is 5/4. So note, hitting probability is exactly the same as discrete time. Expected hitting times, just remember this amount of time spent instead. So that's expected amount of time in current state. That's the only bit that's different. Everything else was the same. Just one last thing to comment on. You'll remember that we also had return times and return probabilities. And this was, don't count, in discrete time we said don't count time 0. What's the probability we come back, or the expected amount of time to come back? But that's a little trickier in continuous time, because we're going to sit in the current state for some amount of time. So we're talking about what's the first time after we leave. So these are all about probability or expected time, which we called mi and mu I, to come back to I after leaving, which is a thing that takes time, exponential qi. There's a slightly annoying thing here, which is if we've got an absorbing state, then we never leave. In that case, we don't need any of these things, so let's just say it's undefined. So let's just say these are undefined for absorbing states, because we won't need them, and it's not really clear what it means to return to a state that you never ever leave. It doesn't really make sense. So for absorbing states, let's not just bother, it's undefined. But otherwise, we sit in I for an exponential qi amount of time, and then what's the probability we come back? So you'll remember that these also had a condition on the first step things. Right, so mi, the return probability is, well, we'll go to some other state j with probability rij, and then what's the probability we come back? If you like, you can write that in terms of rij is qij over qi, if you like. Similarly, mu I is how much time do we spend here? We spend average 1 over qi, because it's exponential with rate qi. The expectation is 1 over the rate. And then again, we'll have to go somewhere else. And then we're asking about the amount of time to come back. It turns out if you want to write that in terms of the qj's, the 1 over qi comes out the brackets in quite a nice way. Sorry, that's 1 plus. qij eta ji. But as before, remember how we said in discrete time, you don't bother to remember these equations. There's nothing worth remembering here. It's always just that you condition on the first step and write down equations and see what you get. And so the important thing was the examples that we saw about remembering that hitting probabilities are the same as discrete time, but for expected hitting times, you just have to remember that we spend a random amount of time in the current state.